Hello, everybody. Welcome to the APS Colloquium. It is a pleasure to introduce Ted Bergin, who is professor and chair of astronomy at the University of Michigan. He obtained his PhD in 1995 and then spent a while as a postdoc at the Smithsonian Astrophysical Observatory. It says apparently you were an astronomer in 1995 and then an astrophysicist in 2000. I'm not sure what.
Blame the federal government.
Blame the federal. Okay. We continue to do that. In 2003, he joined the University of Michigan faculty. And in 2015, he became chair. And still here he is 8 years later as chair. Unless you're going to tell us you're going to step down.
I am.
In 2008, he won the University of Michigan's Henry Russell Award for Exceptional Scholarship and Conspicuous Ability at Teaching, one of the highest honors for junior faculty. In 2019, he won the Danny Heinemann Prize of the AAS and the AIP, quotes, for his pioneering work in astrochemistry and the chemistry of stars and planetary formation, and for his tireless efforts to improve diversity and inclusion in astronomy. I notice his teaching credits include Astronomy 106, Aliens, and maybe we should have a course like that here.
Very popular.
Ted came to my notice because of a New York Times article this summer, right? Talking about the first detection of what I thought was a cation, apparently is a cat ion. I didn't know that cats could be ionized in protoplanetary disks detected with a JWST. So, Ted, go ahead. You have the floor. Thank you very much for coming.
Sure, my pleasure.
Let's give him a
hand. Super happy to be here. It's been a fun visit. So I'm going to talk to you about planet formation today and how we try to understand formation from the formation perspective and link it to the observed exoplanet population, particularly the compositional aspects. The two parts of my talk, I should acknowledge my collaborators. I'm going to talk about a large ALMA program. I'll give the full names at the end, but it features work from Arthur Bosman, who has sadly left the field, but he was amazing. Jenny Callahan, former student who's now at Harvard as a postdoctoral fellow, John Ellie, who is at Leeds. This is a current student, Maria Colmenares-Diaz, and Richard Booth. And the second part of the talk, we'll talk about actually how you make the Earth and the potential implications for that. This is a collaboration with geophysicists, astronomers, and so on. And I'll explain more about that as we go. All right, so I'm an astrochemist, so we're going to talk a lot about molecules here. And what I'm trying to understand is look for signatures of planetary birth. Can I learn about how planets are born from looking at the compositional aspects, understand maybe how chemistry could influence planet formation, but ultimately what you're after is life, right? And obviously water is a key aspect for following the trail of water. I'm actually not going to follow the trail of water. I'm going to follow the trail of carbon. That'll be the second half of the talk. And I want to acknowledge that I don't have the answers. This is a very dynamic and exciting time. So stars are born in molecular clouds that collapse under the weight of their own gravity, probably induced by things. Centers then get overdense, collapse again, make a star, here, disk, accreting material, outflow comes out. Eventually the flows ablate the surrounding envelope. You get a planet-forming disk. Planets are born in this disk. And of course, we're in an amazing age of astronomy where we can actually see all of these things all at once, right? So we have our clouds. This is a pre-stellar core. You're looking in N2H+, which is a weird molecule. I could talk about it. This is millimeter continuum. So the dust grains grow to about millimeter sizes. They sink to the midplane. That's the seeds of terrestrial planets. That's CO. You're looking at the flared surface from a Hubble Space Telescope image. There's the jet. That's an ALMA image of these millimeter grains looked in a different way. And you see these gaps here that we think are due to planets. We don't quite know. So this is Planet Formation 101. Planet formation has undergone a bit of a interesting theoretical leap in that we think that planets, we used to think, you build up bigger and bigger things, and then it was bigger things banging into bigger things. There's a change in things, and that we think actually the pebbles matter the most now. So the dust in the interstellar medium grows to about millimeter, centimeter sizes in the disk. Those pebbles then are the seeds for planets. So some magic happens, and you get to some planetesimals. The current theory is something called the streaming instabilities. Planetesimals are sitting in a sea of pebbles, and it's actually more efficient for those planetesimals to grow, not by accreting other planetesimals, but by accreting pebbles. And so it gets really amazing. So you have the pebble growth phase, and then you have this is what Hal Levison over at Southwest Institute used to call this is the pebble, and this is Bam Bam. So the phase where everything's banging into each other, and then you get to the Earth. But there's other paths here. You could grow to even bigger stages via pebble accretion. Maybe you capture gas. And another possibility, of course, is there could be direct gravitational collapse on the way to making giant planets. So to focus on this concept of linking planets to their birth, I want to look at bulk composition. And there's two ways I'm going to do this. I'm going to use the Ceto ratio, and then following the carbon and thinking about the Earth formation first, because the Earth is where we have the best data, and then take what we have from the Earth and then extend that elsewhere. So just to give you an idea of the bulk composition carriers for carbon and oxygen, you have what I would call the refractory, the things that are hardest to pull out. So there's amorphous carbon grains, silicates, of course, are where the oxygen is. And then you go to the things that are slightly more volatile but still kind of refractory. That would be the polycyclic aromatic hydrocarbons or the aliphatic, so carbonaceous grains from the interstellar medium. And then the true volatiles, the things that most likely want to stay in the gas. CO, CO2, water would be in that concept for oxygen. So those are the things that we want to try and follow. And of course, this concept is based upon the sublimation, where and what temperature you transition from the solid state to the gaseous state. From the perspective of a terrestrial world, right, we're made out of the solids. And so if it's in the gas, it didn't make it into the planet. Now that's not true for a giant planet. But you can see here, CO is the most volatile substance at 30 Kelvin, and then CO2 has its sublimation temperature here at 60, then water, then the semi-volatile carbon, and then the true refractories. And that is a guess as to where these lines might lie in the solar system. So first talk of the talk is going to be the Ceto ratio, and this was a paper by Karen Oberg, Ruth Mary Clay, and myself, where you have the carbon to oxygen ratio versus radius, and you have different sublimation fronts. So that is, it's colder further from the star and warmer closer, so you're really far from the star. Well, CO, CO2, and water, these are the main carriers that are able to cycle in between the gas for the most part. They have different sublimation fronts, so that means the Ceto ratio will change as a function of position in the disk, both in the solids and the gas, right? And if you think of the primary method where we think giant planets form, that is, you form a many Earth mass core first, and then you accrete the gas. What you have here is the solid core formed first. It's made out of this stuff, and the envelope here forms out of this stuff. And so maybe, just maybe, you could look at the Ceto ratio in a planet, and you might be able to tell its birth location in the disk. It's more complicated than that, because after the planet is born, a giant planet, it could still accrete pebbles or planetesimals with this kind of composition, and you could lead to changes. So that's the concept. And so the way I'm going to explore this is using the Atacama Large Millimeter Array, where we can observe both the solids and the really, truly volatile stuff in the gas. What you're looking at here are 5 disks in the dust millimeter continuum emission. This is the pebble distribution, if you will. And you can see different. This one shows spirals. This one has actually, that's a big gap. This has huge gaps. And so these are interpreted as being induced by hidden planets that we can't see. Maybe that's true, maybe that's not. We're looking for those planets with James Webb as we speak. And so this is the distribution of dust, and I'm going to talk to you about the distribution of the gas. And so this program observed those 5 disks in about, I think it was 14 different molecules, 29 different transitions. And you're looking at CO here. There's a different disk in this direction here, and a different molecule going up here. And I'll just let this kind of play out. So the simplest molecules, there's CO and there's C2H. You start to see rings in the molecular emission. These are more complex, CH3CN. The bigger molecules, which are still pretty small, are more centrally concentrated. I love this one. You can actually see the bowl shape of it. So this is now revealing just one of those disks. This is HD 163296, so it's an A star disk. And you know, this is about 400 AU-ish, something to say. All the different molecular phases of this system. And you can see CO is much more extended. These complex molecules, not very complex by life standards, but by interstellar standards they are much more centrally concentrated. And buried in this is, you know, information about the composition of the disk itself. Makes sense when you have all this data. And so the tracer that we use for the C-O ratio is C2H. So this is a hydrocarbon. And you're just looking at, again, the millimeter continuum emission from the disk and then one of the rotational transitions of this molecule. One of the goals of this program was to look and ask, is the chemistry in some way related to the structure that we see in the solids? And the answer is yes and no. Because it's astronomy, right? It's never linear. In some cases, it seems to. In other cases, it's not. And the way we extract information in terms of the bulk composition is using models. So what we do is we use essentially a thermochemical model where we construct a forward model of the system, its density and temperature, using the data that I just showed you along with its overall spectral emissions. That's the spectral energy distribution. Construct a model of the dust density and temperature structure using a dust radiation transfer. And then you do basically a coupled chemistry and thermal physics to solve the chemistry and the gas physics simultaneously. And that's actually the propagation of the UV field in one disk with a big gap in it. The disk was kind of like a brick wall and stuff was kind of bouncing off of it. In any event, we get this density and temperature along with abundance structure, and then we can make predictions, and each of these are predicted ALMA emission images of the dust, the gas, or we can do Spitzer and James Webb as well. And so that's what we did for this thing. It's Arthur Bosman's work. This is again, the dust and the gas. We constructed basically column density radial profiles. So that's the radius, column density. That's this line here, okay? Actually, this one right here, the red one, okay? And these are different models where we change the C-O ratio. And so in this disk, the C-O ratio appears to be greater than unity. This is an upper limit to what's going on in the inner disk. Okay, so that's one system. We did this for a bunch. One problem we have is that the C2H, we can actually see this, is often emitting from higher up in the disk, and the planets are born in the midplane. So how can we approach that? The way we do that is using these other molecules, and I'll call out this one right here. This is methyl cyanide. Methyl cyanide is a symmetric top molecule. It has 2 rotational axes. We won't get into too much about it, but these molecules turn out to be amazing thermometers. It's a really super cool aspect of molecular physics. And this is basically, again, the column density, the statistical weight. This is essentially flux, if you will, versus upper state energy. And you can see we can get a straight line here. And in this diagram, when you get a straight line, it's basically the temperature of the gas is what that slope is. And this thing is 35 Kelvin. It's emitting from within 50 AU next to an A star. The disk is hotter up top, colder down below. So this molecule has to be emitting closer to the midplane. It just has to be. And so I had a student, this was Jenny Callahan's work, where she fit this over a year. I think she was going to kill me. This was really hard work. So the emission is shown as these sort of, with the error bars, so that's why it's kind of scattered here, are these lines here, and the dotted lines are the models. So this is different, this is one molecular transition of CH3CN, another one, this is HCN, and this is HC3N. And the upshot is that the CETO ratio that we measured for C2H appears to be going all the way down to closer to the midplane. Okay, also CETO greater than 1. So this is where we are. This is the state of the field today. This is the CETO ratio in as many systems as we can measure it. Also shown with the CETO ratios that we measure for direct detection planets. Most of these are HR 8799 along with one or two others. And then there's a couple hot Jupiters thrown in there. This obviously will grow. And this is there was a survey of C2H, and this shows the range over which the CETO ratios that were shown for that, but there are some systems where there are upper limits. Maybe they're smaller disks. We don't know. But the upshot is these two things don't look alike, right? The gas, the CETO ratio in the gas in the disk appears to be greater than the CETO ratio in the gas in the exoplanet atmosphere. Okay. Now, one possibility is that these are the younger systems, and they appear to be somewhat closer to the direct detection planets in terms of their CETO ratio. So maybe there's an evolutionary effect we're observing here. I don't know. But actually, if you look at these, I don't really see a difference between one or two in this diagram. You still have to get a lot of oxygen to go down here. Okay. Another possibility is these direct detection planets are all around A stars. The A stars on this plot here are this one here, AB Aurigae, and these two up here, MWC480, HD163296. All the other ones are basically K stars by and large. Okay, well, of these, these two have a high CETO ratio. This one appears to be maybe closer to that, but we don't have a measurement from a tracer that gets me closer to the star, so I just don't know. So what does this tell us? Okay, another thing is that when we're measuring the abundance, basically, if you want to think about it this way, the CO snow line for all these systems is somewhere like, say, like right here. All right, and so the CETO ratio in this gas should be unity, but for these systems, it's greater than 1. And even in the systems where the CETO ratio has been measured with C2H, we also seem to be missing some CO from the gaseous state. That is, the C to H in the disk gas appears to be slightly less than the star. So what does this mean? Well, put simply, this is a plot of the CETO ratio in the grain versus what the CETO ratio would be in the gas, if a CETO 1.25, 0.551 or 2, versus how much carbon is in the gas, the C over H, if you will, okay? And the C over H's we seem to be measuring are somewhere in this realm here, okay? And the CETO ratios that we're measuring are CETO ratio of 1 or 2. What that says is that the grains have solar or stellar composition. It makes sense. The grains have the oxygen, okay? And they actually have a little bit extra carbon too. So to make these direct detection planets, they can accrete that gas, and the only place they can get that oxygen, because they're not getting enough oxygen when they accrete gas, is by swallowing a lot of pebbles or a lot of planetesimals. That's it. And so that's which of the two it is. I'll be agnostic because I'm not a dynamicist. If I read the papers, it seems like pebbles are easier, but we're going to have to figure that out. So the future of this is there's lots more to do. I've sort of summarized the state of the field right now. That was 10 ALMA cycles, a lot of work to get to that plot with just a handful of data points, right? Same with the exoplanets, right? But we have an ALMA large program. We're observing 90 sources, and this is the dust emission maps from 77 of those. This is being led by Ilse Cleaves, called the ALMA Disk exoplanet connection or C over O ratio. So the detection statistics for the dust are quite high. For C2H, which is our tracer of C to O ratio, appear to be like 65% of these systems. So we're going to get decent statistics on C to O ratios within the next year, which is insanely exciting. All right, now I'm going to seg and transition and talk about the inner few AU. So everything I was talking about with ALMA, we can observe disks in the gas into radio about 10 AU. All right, that's where we run into just the resolution limit, right, and a sensitivity problem. The dust you can get to 3 to 5 AU because you're integrating over greater bandwidth. So you're not doing the terrestrial worlds with ALMA. And indeed, the place where we have the most data for terrestrial worlds is this wonderful rock that we're sitting on. And here we are, we have this wonderful carbon-based living planet with all that green on it. And if you were to take all that green and ask how much carbon is on the surface of this planet, that's it. Okay, we are a carbon-poor world. All right, if you want to look at what was available, we got less than 1 carbon atom per 10,000 available, less than 1 nitrogen atom per 100,000 available. Water, we are a water-poor world. At most, by mass, we are 0.1% water, at most. Okay, we are a carbon, nitrogen, water-poor world. We are a silicate rock. And is this common? What does that mean for life? Well, I guess it's good, right? But is this common? And how did this happen? All right. So this is the data that gave rise to that little simulation that I did sitting at my desk trying to figure out the numbers. So what you're looking at now is the carbon to silicon ratio. So before I was thinking of carbon to oxygen, or maybe I was doing carbon to hydrogen. Rocky worlds, right? You're silicates. So normally the geo people normalize the magnesium. I can't do that because we think of silicates. So my brain, as an astronomer, I have to do it normalize the silicon. So this is the carbon to silicon atomic ratio. There's the sun. This is the number that I gave you there. All right, so you can see that disparity. Now, when the Earth was young, it went through a magma phase, right? And the carbon in that magma ocean, under certain conditions, would react with the iron and be carried to the core. So it may be that most of the carbon in the Earth is in the core. But if we actually, my geophysicist colleagues went and it was Jackie Lee at the University of Michigan, we asked, well, looking at all the geophysical and geochemical constraints, how much carbon could you stuff into the core? And so this is the true upper limit for what the Earth is. The Earth is a carbon-poor world. If you go to the outer part of the solar system, comets have basically all the carbon that you would expect. And in the interstellar medium, about half of the carbon is in refractory form, some sort of solid state form. All right? That stuff did not make it into the inner solar system, because if you look at meteorites, which are tracing the asteroid belt, even the most primitive meteorites that otherwise trace the composition of the sun, in fact, in some cases we use them to tell us what the composition of the sun is, are depleted in carbon. They are carbon poor by about a factor of 20 on this, in this framing. Okay? So this is what tells you that there's a carbon problem in the solar system. Something has to happen to this stuff so it doesn't make it into this. Okay, well, this is the data. Actually, if we look at what we know about where the carbon is from ALMA and mostly Spitzer, but now James Webb, because it's giving us the ices, you find about half the carbon is in some sort of refractory form. That carbon, that refractory carbon, may have come from evolved stars, but it actually may be made in the dark cloud itself at 10K. We actually see PAH emission. Identified PAHs have been detected in 10K dark clouds that are the pre-stellar stage before star birth. So some of this refractory stuff may be made basically right before the star is born. Okay, so half of the carbon's there, then you got methane ice, mostly CO, CO2 ice, and all the organics that matter are a tiny amount. So if I go to this framing here, okay, about temperature, and I look at, well, what goes where, in terms of the solids, okay, if I'm out here in the Neptune-Uranus zone, well, this, explains why Neptune has a lot of carbon, right? It has those methane bands and so on. Okay, if I move a little bit inward inside the CO zone line, it makes sense, right? You lose the CO. And if you go to, where Jupiter is born, well, I lose most of the carbon except for this truly refractory stuff. And then if I move here to 1AU, given the temperatures of what we think we know about in the disks out of which planets are born, so this is temperature here versus distance, this is what you would get. This is in the habitable zone. This is where the carbon would be and where the oxygen would be. The problem comes is if you look at the numbers. All right? If the Earth was made of this stuff, we should have had a carbon to silicon ratio of 5, whereas we're much less than that. We should be sitting on a carbon rock with 0 water, but we're not. Okay, so how did that come to be? Okay, so back to this plot. This says something happens to interstellar carbonaceous grains, leads to this, and something also happens during planet formation. And I'm just going to talk about the first part, but I'm happy to discuss the second part if anybody has any questions. Okay, so we're going to think about planet formation just from a simplified perspective. We're going to have the true refractories, that's the metal and the silicates, and the things that might cycle into the gas. And that would be the solid state organics. I'll refer to that as soot through this talk just to give you something that your brain focus on. It's actually not soot, but okay, it's less volatile than soot. Water ice, and then of course you could accrete hydrogen from the gas. All right. So the Earth is made of this stuff, right? The metals and silicates with small amounts of that, and of course we believe we had initial hydrogen atmosphere that dispersed fairly early on in the Earth's. So the Earth is formed from refractory materials, the small of this stuff, small amounts of water. If we think about going back to my initial framing of the Ceto ratio and the various ice lines, the Earth is a water-poor world in the aliens class. The Earth formed inside the ice line. The Earth is a carbon-poor world. The Earth formed inside of the soot line. Okay? So that's that all well and good. It does present a problem, though. My soot line here is somewhere around 500-ish K, maybe a little bit less. All right, if I look at all those disks that I showed you those nice millimeter continuum images of, we can measure the temperature of those pebbles. And those pebbles are the seeds of terrestrial planets, right? We're looking at stuff that matters here. That's the blue line. They are in what we call the radiation-dominated regime. That is, if you have a few million-year-old disk, the star is dominating. All right, and it's resulting in the heating of the disk itself. And your soot line is way up here, not at 1AU. And whatever this is, it has to operate all the way out to the asteroid belt because meteorites are carbon poor. My soot line needs to be out here. All right? And the only way that can happen for the materials that make the Earth is if you go to earlier stages where there's still envelope accreting onto the disk and there's additional accretional energy in the system. All right? And so that's what's shown here. These are different just models. With a typical accretion rate of 10 to the minus 8 solar masses per year, you have more energy. The soot line goes further out, as does the water ice line for that matter. Okay? And that's 10 to the minus 7. And I can put that in time scales. This is greater than 1 million years. This would be less than of order 1 million years. So what's happening here? I have my star here. There's my soot line. In the radiation-dominated regime, I have a population of carbon and silicate grains. They may not be separated here. They may actually be together, mixed together. In the earlier stages, there's more energy. The soot line gets pushed out. and you have silicates with very little carbon at all. And the Earth has to be made out of this stuff. Okay, so there's the concept here. Now, this actually makes a true carbon-poor world, which is one problem, but there's an even bigger problem. And that is that the disk is rotating, okay? And the gas, because of gas pressure gradients, is going at a rotational speed that is slightly offset from Keplerian. The dust doesn't see that pressure gradient. It's in the midplane, all right? And it doesn't have that own pressure gradient. And it's rotating at Keplerian. And so there's a slight drag force on the dust that causes the grains, when they reach to a certain size, they become partially decoupled from the gas. And they drift inwards. And the millimeter and centimeter sized pebbles that we're observing in ALMA are in this sweet spot. And so there's a constant supply of carbon from the outer solar system going to the inner solar system. I think about this, the nearest system, TW Hydra, its CO disk is 200 AU in size. Its dust disk is 60 AU in size. Now that could be drift. It could be due to drift. Also, the disk could have viscously spread. But in the concept of where it was drift, where did all that dust go? Right? Where did it park itself? And it's possible it parks itself at 1 AU. We don't know. So one way to do this and to stop that drift is to have a planet be born. Actually, what you need is just a pressure bump, a slight reversal in the pressure. The dust is drifting to the pressure maximum. And if you have a pressure reversal at any point, the dust will pile up at that reversal. And indeed, there is some information from meteorites, cosmochemical information, I think is the framing that I want to say, that suggests that the solar system was separated chemically, and carbon plays a role in that as well. So we have Jupiter, or whatever led to Jupiter, and that breaks the system up. That gives us perhaps a little bit of carbon, or maybe you have some redistribution of this material here that gives us additional carbon later on. But the key point is that the Earth has to be made out of stuff there. Now, that doesn't mean that the Earth was formed in 1 million years. What that means is that planetesimals must have formed within 1 million years. All right? That is, the composition was fixed in rocks where it's hard to lose the volatiles from. Okay, it's easy to lose volatiles when things are small. When they're really big, it's harder for them to devolatize thermally. There's other ways, trust me. I've been educated. But there's another interesting question, that is, what happens when you don't have Jupiter, right? Okay, so just again summarize, the material that made the Earth was fixed in composition during the protostellar phase. To reduce the carbon content for the Earth, we need Jupiter, or whatever led to Jupiter, or something to stop the supply. So I want to ask another question then. So I have this interesting concept or reimagining of planet formation. I have my ice line, there's the soot line, the silicate line is here. What happens when you have a planet that's born there? That's got carbon, it's got silicates, it's got metal, it's got no water. Why does this matter? Well, if you look at all the planets that we have detected to date, most of them are super Earths and mini Neptunes. That's the radius distribution shown there. Okay, these lines show the mid-plane temperatures towards measured by ALMA for a handful of systems. Now I can put more on there. Some are slightly warmer, some are slightly colder. But the key point here is here's the ice line, here's the soot line for where these planets are. If they were born in situ, which they may not have been, they may have been born out here and then migrated in. But if they were born in situ, they're in this magic zone. Now, if they weren't born in situ, I just gave you a nice little song and dance story saying that it was warmer younger, right? So yes, it's complicated, but this may matter. Okay, so we're going to look at this. and ask the question, well, what do these planets look like, these soot-rich planets? And again, this is work done with the collaboration of some geophysicists, Mark Hirschman, Jackie Lee, myself, and Jeff Blake were the astrochemists. We have a planetary science, Fred Chesla, and Eliza Kempton is our exoplanet expert. So we're going to look at planets that are 0.1 or 1, 0.3, 1, and 3 Earth masses. They're made of them. They're silicate-rich worlds. We add a little bit of soot. All right, we're going to take a model where we add no water, add a little bit of water. This is what soot is made of, if you will. So hydrogen is coming. You can make water from the system. You need hydrogen, okay? And the bigger planet will accrete a hydrogen-rich envelope. Then we solve for a molten mantle and the overlying equilibrium. That's my geophysical colleagues. And then Eliza takes that and does an equilibrium chemistry for pressure, temperature. And we suspected that this mantle would probably be rich in hydrocarbons that would then outgas. And so we suspected that maybe you can make hazes. So we have a model of haze formation. And then we predicted what they would look like with Webb. Now, just to give you an idea of the landscape, for things that truly form beyond the soot and ice line, that's comets. All right, they are 20 to 40 weight percent, that is, of their mass. Their 20-40% is carbon, okay? What we're doing is we're adding a tiny little amount. We're assuming carbon loss. But we have silicate-rich worlds with more carbon than the Earth has. This model is for young planets. I'm doing magma equilibrium, okay? So for Earth-like worlds, we have to talk about 3.4 billion years of evolution, plate tectonics, all that other stuff. But the 3 Earth mass planets that has a H2 envelope, this is more representative of what's going on. And that's what I'm showing you here. So these are 4 different realizations of this model for the 3 Earth mass planet. There are different models of how much soot we add versus water. It doesn't matter. The end result is we have a hydrogen envelope around this 3 Earth mass planet, and the atmosphere has methane in it. And the 4 different models there are different temperatures, which are meant to be how far the planet is from the star. Okay? So these planets are methane-rich, methane-dominant atmosphere, and we actually showed very nicely that they produce hazes in the upper atmosphere. And just to show what they would look like, if we have, this is the transmission spectrum. With the haze is the yellow here, and without the haze you see the methane features. And we looked at this, and the haze formation is fairly robust, adding even when you add lots of water. Now, this is hard to do with James Webb. 3 Earth mass planets is really at the limit or below the limit. So we have to push our model to higher masses to explore the additional implications of this. But there's another way to look at this. All right? That is, if the carbon is not in the solids, it's in the gas. And maybe I can observe that. Okay? And this is a James Webb spectrum. So flux, wavelength here. This is basically 14-ish microns, give or take. This one system, paper just came out where they see a hydrocarbon chemical explosion, including a detection of benzene, which is the simplest PAH in the gas. And their interpretation of this is that the carbonaceous grains are being destroyed in this system, and the planets that are born in the system will be carbon poor, like the Earth is. And how common this is? Well, you know, I think within a year or two we'll have 400 spectra similar to this. And so what you're looking at there is a better realization where you actually have the wavelengths, and you can see that this huge optically thick, massively optically thick acetylene feature suggests there's a substantive amount of carbon in this system. And the future, frankly, is this, right? Here's the Ceto ratio that you would estimate in that system, okay, for the inner few AU, which is where James Webb is coming and tracing. So with ALMA, we can get into 10 AU. James Webb, we're seeing that emission is coming from basically 1 to 2 AU. Why do I know that? because it's 500 K gas. And the only place you're going to find 500 K gas in that system is parked right next to the star on the surface of the disk. Okay, and we know it's the surface of the disk because the disk itself has an optically thick dust surface, right? So we're only capturing the surface of all these systems. But you can see that I put here additional systems where we've been measuring the CETO ratio, and there's diversity. And maybe time dependence, I don't know. But there's an awful lot more to do here. So in this part of the talk, I've given you sort of a reconception of planet formation. And I think these volatile-rich, carbon-rich planets likely exist in the exoplanet inventory. They're out there. We just haven't recognized it yet. One implication of that is these are natural sources of hazes for sub-Neptune-like worlds. And indeed, hazes are a common feature for sub-Neptune-like worlds. What does this mean for habitability? Ooh, super interesting question. Lots of work to do there, interdisciplinary work. And what titrates this flow of carbon? Can we detect the solid state carbon being released? It's all so much fun to do, and there is all the collaborators. And I'll end there and take questions. Thank you so much.
Usually like to invite our students to ask the first questions. So questions.
Hi, so you had a plot at the beginning that was the carbon to oxygen ratio, and on the x-axis was the radius in AU, and there was those like vertical lines where it was like H2O, carbon dioxide, carbon monoxide.
Mm-hmm.
I was just wondering if you could expand like what that means specifically, like why it says H2O and all that there.
Sure. So I'll break it down. So we'll start here. All right, so for a typical disk that's in the radiation-dominated zone regime, that's a protoplanetary disk. We call those class 2 disks, all those ALMA images, okay? The soot line is super close to the star, so we don't worry about that. So the only thing that's going to be, the only things that are going to titrate the carbon-to-oxygen ratio is water, okay? Over here, CO and CO2. And the neat thing is, well, the CO is here, and the CO and the CO2 also carry oxygen, right? So, okay. So then, okay, if I go out here, okay, CO is in the gas, okay, if it's 40 K, all right? CO2 is in the ice. Water is in the ice, okay? So, this is that concept just placed into a plot, right? So here's my CO ice line right here. The CO is in the gas. The CETO ratio is unity because the carbon is in CO and the oxygen is in CO. And there go over here, I basically have water and CO2 as ices. And then I go interior here, the CO2 ice line, and so on and so forth. ALMA is accessing here, Webb is accessing here. Okay?
Thank you.
You're welcome. Sorry I didn't do that right away.
Kevin.
Thanks, Ted. Nice talk.
Thanks, Kevin.
I'm a student of life. So on your big CO to H CETO ratio plot, you talked a little bit about young disks versus old disks, and I mean the other big time scale there is that all of those planets are old.
Yeah.
This is an ill-formed question, but we know that atmospheric escape changes the at least the amount of material in the atmospheres of a lot of those short period planets. And even on old hot Jupiters, we see carbon and oxygen escaping. Is it possible that something in the planetary evolution could be changing the the distribution between what we see for the protoplanetary disks?
I
and
mean, maybe. I mean, for the hot Jupiters, that's a good question. But you know, the true comparison here is the direct detection planets, where you know that escape process is not as important, right? And no matter how you slice it or dice it, you're losing hydrogen more so than you are probably the carbon and the oxygen, right? And so the other way, I frame this as C over O. The other way to look at it is C over H and O over H, and that axis should betray some aspects of that evolution if it exists.
Next question from over here. So the soot line in our solar system must have been somewhere near the outer edge of the asteroid belt.
Yeah.
And you talked about the inward migration of that material when the disk is still present. But after the disk was dissipated, you still have that carbon-rich asteroidal material. How much radial mixing do you think was really important for the transport of both carbon and water? Because that didn't seem to be in your diagrams for that inward transport.
No, because it would be twice as long of a talk. Yeah, so if you have Jupiter, you know, one of the interesting models is the Grand Tack model, where Jupiter and Saturn go in, stir everything up, and then tack back outwards again, which is really phenomenal. That leads to significant dynamical stirring. Just Jupiter sitting in place leads to dynamical stirring. My answer to that is dynamical stirring was clearly present, and the meteoritic record, the cosmochemical record, appears to require it. From the astronomical perspective, I'm not certain. I can't point to something that says to me. My gut says that the most important stuff is what happened earlier, but I can't prove that per se. Okay.
So we know from observations that most of the mass of a star is accumulated during accretion bursts, short-lived bursts of large accretion. That causes the luminosity to increase dramatically after the Orionis phenomena. Do you consider that, and what is the role of accretion bursts in these models?
Yeah, you're absolutely right, John. So the concept would be that those bursts are probably the most influential to the volatile content for what gets provided to terrestrial worlds. And that's what makes it complicated, because the bursts come at different frequencies, depending upon who the heck knows what. It looks like, you know, the stronger bursts happen more frequently earlier. They presumably are the most influential than the ones that happen later. But you are absolutely right. The next step in this is we want to take, you know, full-up models, pebble drift, and include some sort of luminosity evolution of the system that is stochastic. But then you need to run lots of different ones.
Hi, I was really interested in the connection between the accretion-dominated and the radiation-dominated soot lines for the really, really young systems. And I was wondering, would observations of the magnetospheric accretion radius for very, very young, large numbers of very, very young systems potentially help to confirm that that is actually the case?
That's a good question. I'm linking the real inner disk to what's going on. I think, you know, it relates to what John was saying, right? If it's the outburst, then it's a variable magnetosphere. The accretion, the inner edge, is shifting in and out, and so these things are all related. And I think it's another piece of the puzzle. Is the way I would say it. Okay. The beauty of this is we spent with ALMA 10 years trying to observe the class 2 systems, the disks, because that was the epoch of planet formation. And that is true for giant gas-rich giant planets. But I think for terrestrial worlds, it's the younger stages that matter more.
Thank you.
Thanks for your talk, Ted. I had a question on your simulated JWST observations for those planets. Are those supposed to be simulated for the very, very young ages, or do they take into account some additional evolution?
We made an argument that for the 3 Earth mass planet with an H2 envelope, that the evolution may not matter. We could be right, we could be wrong, but they're a young planet, strictly speaking.
Can you go back to the forward modeling slide, maybe in earlier half? And,
You're going to have to ask your brother about that then.
oh yeah. Oh yeah. Are there any? I'm studying ionizing emission from stars.
Yeah.
I mean magnetic activities.
Mm-hmm.
And are there any uncertainty or what's the necessary point for the next
Sure.
step from as an input parameter?
Sure.
Yeah.
So we're astronomers, we're observing surfaces. These are disks, so they're irradiated surfaces. The ultraviolet field has the most flux. Penetrates the least, but it has the most flux. I suspect for the James Webb spectra that we are seeing an ultraviolet photochemical equilibrium, but I don't. X-rays matter here. They can penetrate deeper, and they lead to a slightly different chemistry than would the UV. Probably important as well. Cosmic rays, particles, we believe are excluded based upon the winds and analog to the sun, the solar system. And indeed, when we measure the ionization rates for the deep disk, they appear to suggest that the cosmic rays are being excluded. With that said, for the younger systems, when there's accretion burst, there's individuals out there that are arguing that they may be generating particles. And the particle ionization rates could be elevated during the early stages, and that may or may not be important. So, there you go.
Thank you.
I don't see any hand raised, so if I may, okay.
Question about selection effects. Or most of your sources seem to be single stars, yet most young stars are multiple. So is there some selection effect and bias in here?
Right. So if you want to think about for the second part of the talk, for the terrestrial worlds, the inner disk, maybe not as much, right? Outside of truncation of the disk and so on and so forth. Certainly for the giant planets, there may be some interesting aspects. I would say to you that the radiation matters, but if you're two, M stars, probably not going to be a big deal. But yes, there may be some effects, but I don't think on the Ceto ratio. I bet you if we did it in the binaries, we would see the same thing, but we'll find out. Because DECO has some binaries in the.
On your ALMA source graph,
Yeah.
are you picking those different?
Absolutely, 100%. Yeah. Because yeah.
Not our random.
No, God no. We are biased.
I'm going to ask my question, which is, this past summer there was a little bit of a furore in the New York Times about the discovery of an ionized methane molecule.
Yes.
Can you explain to us why was that a big deal? Why did it get such big publicity?
Sure. So in the 1970s, we detected molecules. And models were developed to explain how those molecules existed. And at the heart of it was reactions between carbon and hydrogen, leading to a cation called CH3+. Every CO molecular cloud image that you've ever seen, that CO formed through CH3+ plus oxygen, making CO. Now, on the edges of the cloud, another mechanism comes into play. But in the deep interior, the CO is formed through that cation, CH3+. People have been searching for it. Very difficult to find. We found it serendipitously in a protoplanetary disk in Orion, which is highly irradiated. And the CH3+ is forming from a completely different mechanism than what's happening to make CO formation in molecular clouds. But it revealed the presence of this molecule, which is at the heart of interstellar carbon chemistry. When I showed you those CH3CN and HC3N, they're being made through CH3+, no doubt about it. So that's why it mattered. It's at the heart of the organic chemistry of interstellar space.
Thank you very much. Let's thank our speaker again.